So far we've talked about acids and bases and how it affects the pH when you add an acid or a base. Recalling that if you add acid to something, the pH will go down, and if you add base, the pH will go up. But if you add something that's neutral, the pH will stay the same. So that we can see that there are changes in pH when you add acid or base to a solution. So now we're going to look at something called a buffer. What is a buffer? You may have heard of a buffer as something in the military where we have a buffer zone, something that slows something down, or it reduces the amount of destruction caused by an attacking army. So that would be what a buffer is. It's something that reduces something else. It doesn't stop it completely, but it does reduce those changes. In chemistry, we're talking about something that reduces the effects of acids and bases so that the pH does not change as much. It doesn't stop all of the changes, but it does slow it down. Have you heard of a buffer before in regular life? Well, you've probably heard of buffered aspirin. We have buffers in our body that stop us from having big pH changes when we eat a lemon. So you know lemons are very acidic, and so if you were to eat one, theoretically your pH should plummet because you're eating a bunch of acid. But it doesn't happen. That's because there are buffers in our body, throughout our body, that keep our pH about the same. Not necessarily neutral everywhere, but definitely keeps the pH the same when you eat a lemon, or if you eat a chocolate bar, which is basic, the pH doesn't go up. So it keeps the pH the same, not necessarily neutral, but the same as what it originally was, even if I add acid or add base. So let's look more into that. So in chemistry, a buffer is defined as a solution that resists changes in pH when there's added hydrogen ion, strong acids, or added hydroxide ions, strong bases. Notice the key word here that it resists changes in pH. It doesn't stop all changes, but resists changes in pH. And again, that does not mean it stays neutral. It just means it doesn't change from whatever the pH is originally. How does a buffer work? Well, buffers work by reacting with any added acid or base to make them become more neutral so that the pH does not change. So in a buffer solution, it has to have two parts. It has to have one part that reacts with any added acid, H+, and another part that reacts with any added base. In these cases, what it tends to produce is more of what was already in the container. In these reactions, we'll see that a weak acid might be produced. Now, that is coming from a strong acid, turning it into a weak acid. That means there are fewer hydrogen ions present in the solution because we've turned it from a strong acid to a weak acid. And the same thing could happen under basic conditions. We could have a strong base, and we're going to form a weak base from that. So how do you change something from a strong acid to a weak acid? Of course, we have to do a chemical reaction. We're not actually changing, in the case of HCl, we're not changing it from HCl into a whole new chemical, but we're separating those ions into hydrogen ions and chloride ions. Because it's a strong acid, we know it's 100% ionized. But if the H plus gets reacted with in something that makes a weak acid, so let's say H plus reacts with F minus, we've now made a weak acid. It becomes more neutral. It's molecular at that point, and so it has fewer hydrogen ions. And that's what we're going to see how these reactions work, is they react with anything that's been added. So if we add hydrogen ion, it reacts with it and removes it from the container. If I add hydroxide ion, it reacts with the hydroxide and removes it from the container. And there are two ways that it can do that. It can either make a weak acid or weak base, or it could form water. And again, water is neutral, so that means that the pH is not going to be changing by adding the water. There are a variety of ways to create buffers, but the two most common ones are to use a weak acid with its salt and a weak base with its salt. So we have a different video that will talk about how to discover if a buffer has the weak acid and its salt or a weak base and its salt. But in this video, we're going to focus on the reactions that occur to create the buffer system. That is, what are the reactions that we're going to see that resist changes in pH by reacting with added acid and added base.
First, let's look at how an acidic buffer system works. For this buffer system, we're going to use hydrogen acetate and sodium acetate as an example. First, we ask what particles are actually present in the buffer solution. Recalling that weak acids are mostly going to be found as molecules with very few ions, we're going to write down that it's a molecule. So we're going to write it as HC2H3O2. On the other hand, sodium acetate is ionic and is completely ionized in water, so it's completely separated. And so we'll see sodium ions and acetate ions, C2H3O2 minus. Now what we're going to look at is what reacts with what. So what particles are going to be reacting with added acid and added base? In order to answer that, we need to know what things are being added. So when I say I add a strong acid to a solution, we're talking about something like HCl, but to make sure that we know we're talking about an acid, it has to have that H at the start. That tells me that we're looking at added hydrogen ion. When I say I'm adding a strong base to a solution, that means I'm adding the hydroxide part of it. It could be sodium hydroxide or potassium hydroxide. It doesn't really matter which base I'm adding, but I know that I'm adding the hydroxide. The hydrogen ion and the hydroxide ion are the things that change the pH. Since a buffer system is designed to resist changes in pH, it must act on the added acid, the hydrogen ion, or the added base, the hydroxide ion, to get rid of those two ions. So let's look at what reactions occur to get rid of those ions. We're going to start with what happens when a strong acid is added to a buffer. Again, it doesn't matter if it's HCl or HI, HNO3, H2SO4, or even if it's a weak acid. The main thing is that H plus is being added to it. So we're going to write the H plus here. And now we have to choose what is most likely to react with. Theoretically, it could react with any of these three particles. But what we're going to find is that there are two parts of the buffer system that make it into a buffer. If you recall, part of our buffer system rules was that we had to have a weak acid and its salt. And when I said its salt, that meant the part that was not the acid had to match on both halves of this buffer. So in this case, we have the hydrogen acetate, that's our weak acid, and its salt is anything with the acetate. So it doesn't matter if I have sodium acetate or potassium acetate or calcium acetate, it's still going to be the acetate part. And that gives us a clue as to what to eliminate from our three choices. So in this case, sodium is not really part of the buffer. The sodium has to be there to be part of the salt and to help dissolve the acetate, but it is not a requirement for the buffer system. So that means the only two items that we're looking at for the buffer system are hydrogen acetate and the acetate ion. Or more generally, in any acidic buffer system, it's the weak acid and the ion that matches that weak acid. So let's write both of them down. So we have H plus hydrogen acetate goes to, we'll write the arrow, or we have H plus C2H3O2 minus our acetate ion, and we'll write the arrow in. So let's look at these two systems and decide which one is most likely to occur. So does it make sense for an acid to react with an acid? Not really, so that reaction does not occur. On the other hand, does it make sense for something with a positive charge to react with something with a negative charge? Hopefully it does make sense to you, and you can probably predict what the product would be. In this case, we have 1 plus and 1 minus. We put them together, and we get the formula HC2H3O2. Notice that that is the same acid that we had to start with. One of the reasons that we have to have that matching system is so that when we're done, we make more of what was already in the container, and that stops the pH from changing. So we can see that when we've added acid, H+, to this acidic buffer system, the acetate ion reacts, and it forms more of the molecular hydrogen acetate in the system. Now, let's look what happens when we add a strong base to the buffer. Again, when we're adding base, that means we're adding hydroxide ion. So we'll start by writing OH minus, that's our first thing we're adding, and we're going to see what it reacts with. In this case, the same exact particles are present, and again, the sodium is irrelevant because it is not part of the buffer system. It will not do any part of the reaction. So again, we're going to write two equations. The first one is going to be OH minus plus hydrogen acetate. Write the little arrow. And the second one is going to be hydroxide ion plus acetate ion. Now, just looking at these quickly, let's see if we can figure out which one will not react. Hopefully, you can see the second one has hydroxide with a negative charge and acetate ion with a negative charge. We can't put two negatives together, and so we know that that reaction does not occur. Well, that leaves the top one. So in that case, we have hydroxide and hydrogen acetate. And recall that in our neutralization reactions, acids and bases like to react with each other, and they like to form water. And that's what we're going to see here. So let's take out the OH and the H, and what will be left behind is actually the acetate ion, the C2H3O2 minus. Make sure that negative charge is on there, because we took away the positive hydrogen from there, leaving behind that negative anion, the acetate ion. So the products formed are water and acetate ion. Again, these are both things that are already in the system, so it does not change the pH. Now let's look what happens when we have a basic buffer system. The example we're going to use is ammonium hydroxide and ammonium chloride in water. Notice that we have the ammonium part matching to make sure that we know that this is a buffer. The ammonium is the part that is not the base in this case. So what are the particles that are present in the buffer solution? So the NH4OH is actually NH3, but we're going to write it as NH4OH just to make it easier to see how things match. That is a weak base, so we expect it to stay together as the molecule. So we'll see that as NH4OH. On the other hand, the NH4Cl, the ammonium chloride, is ionic, and so it will separate into its two particles, NH4 plus and Cl minus. When we look at this system, what part makes it into a buffer? That should be the ammonium hydroxide, and the part that is salt, its part, is the ammonium ion. So the chloride will be ignored for the rest of this section. So let's see what happens when we add a strong acid to this buffer system. So recall that a strong acid means that we're adding H plus to the system. That's the thing that's going to change the pH. The choices that it has to react with are NH4OH or NH4 plus. Let's write H plus NH4OH and H plus NH4 plus. Hopefully you can see quickly that those two on the bottom will not react because we have two positive charges. So we know that that reaction does not occur. Now let's look at the top reaction. For this, we have the acid, the hydrogen ion, and ammonium hydroxide, a base. Recall that acids and bases react well in a neutralization reaction. So if we take the H plus and the OH minus and put them together, we get water. And the byproduct of this will be NH4 plus. Again, the ion that is part of the buffer system that we saw earlier. And that is how the hydrogen ion that's being added is removed from the system, keeping the pH the same. So what happens when we add a solution of a strong base to this buffer? When we add base, recall that that means we're adding hydroxide ion. It has two choices. It can react with ammonium hydroxide or the ammonium ion. If it reacts with ammonium hydroxide, we're going to have hydroxide reacting with hydroxide. That doesn't make sense. For the second reaction, we have hydroxide with a negative charge that could react with ammonium with its positive charge. We put those two together and we get ammonium hydroxide. Again, the thing that we saw earlier, that is our weak base. It was already in the system, and this is how the hydroxide is removed from the system and is left as a more neutral compound, as the molecular compound NH3, or as NH4OH in this case, and that is going to keep the system the same pH.